Okay, so this is Advanced Applied Analysis, Lecture 11, Math 466. So what we're going to do today is we're going to prove what the Fourier transform of the Gaussian is. There's a lot of integration that goes on here. There's a lot of different ways of looking at these results. And so what I want to do is I want to spend today doing a somewhat technical integration-heavy lecture within reason. What I will often do is I will specialize and say, look, let's look at the standard normal. If we adjust and put in the variance, we just have some sigmas that propagate throughout. I really don't want to have to deal with that. You can figure out how to do the change of variable at the end of the day. When you have something like this, you want to try to keep the algebra as simple and as clean as possible. Okay, so what we're going to first do is we will first start off with some of the needed results about the Gaussian. So if we do the standard normal, normal 0, 1, the density is f of x is 1 over square root of 2 pi e to the negative x squared over 2. Have you seen the polar trick to integrate this, to find that this integrates to 1? Okay, so we want to integrate from minus infinity to infinity of f of x dx. What we're going to do, let's call this I. So what we're going to do is we're going to look at I squared. So that's going to be the integral from minus infinity to infinity, 1 over square root of 2 pi e to the negative x squared over 2 dx, integral from minus infinity to infinity of 1 over square root of 2 pi e to the minus y squared over 2 dy. And we want to show that this integrates to 1. And in fact, that's why we have the square root of 1 over 2 pi looking outside. We can't use the same dummy variable of integration twice, or if we can, it's a really bad idea because it will be confusing. So let's use x and y. So this is a double integral. I can bring out 1 over square root of 2 pi, 1 over square root of 2 pi, and I get 1 over 2 pi. Now I have a double integral, minus infinity to infinity, minus infinity to infinity. And I'm going to write this as e to the negative x squared plus y squared over 2 dx dy. And as we're looking at this, what do you think of as soon as you see x squared plus y squared? Polar coordinates. And in fact, the reason this integral is so bad is if you want to integrate e to the minus x squared over 2, you would want an x dx, not a dx. So if we now do polar coordinates, this is 1 over 2 pi integral r goes from 0 to infinity. Theta goes from 0 to 2 pi, just because of the order we write things. Integral r goes from 0 to infinity, e to the negative r squared over 2 r dr d theta. And so we've just done polar coordinates. The d theta integral, there's no theta dependence here. That's nice. That's just a 2 pi that cancels with this. The r integral, well, we want a negative 2r over 2. We want a negative r. We have an r. Great. All that means is we get e to the negative r squared over 2. We flip the order of integration. So this will just be e to the negative r squared over 2 at 0 and infinity, which is just 1. So we know that I squared, our integral squared, is 1. What must I equal? Minus 1 or 1. Why can we eliminate I equals minus 1? It's possible. Maybe this integral is equal to negative 1. Why do we know this integral is not negative 1? What are we integrating? Well, we don't know its probability distribution yet. But I think you're about to say, what must be true about a probability distribution?
That has to be positive.
So we're integrating a non-negative function. If we integrate a non-negative function, we're not going to get a negative number. So this tells us I is either minus 1 or 1. As it's non-negative, it implies I equals 1. So this is probably the most famous, most standard way of finding the integral of the standard normal. And if you have a sigma, you just do some bookkeeping to find out what goes on there. Okay. Another thing that's very useful is the gamma function. So gamma of s is the integral from 0 to infinity of e to the minus x, x to the s minus 1 dx, at least if the real part of s is greater than 0. So you always want to make sure that your integrals exist and are well defined. So as you go off to infinity, we have exponential decay here, and at most polynomial growth. No problem at infinity. The danger is near x equals 0, what does e to the minus x look like near x equals 0? So when x is very close to 0, what does e to the negative x look like?
Very large.
When x is close to 0?
It looks like
Yeah, it looks like 1.
Yeah.
So near x equals 0, this looks like 1. So this looks like x to the s minus 1. We want to make sure this is integrable. So if you think of s as a real number, I need s to be greater than 0 so that when I integrate this, I'll get x to the s. I mean, I don't want something that blows up. If x was negative 1/10, when I integrate this, I would get x to the negative 1/10 over 1/10. And then that would blow up. So that's where the real part of s greater than 0 comes into play. With a little bit of algebra and integration by parts, you show gamma of s plus 1 is s gamma of s. And in particular, if you take an integer n plus 1, you get gamma of n is n factorial. Gamma of n plus 1 is n factorial. It's a little bit annoying. It's the factorial function shifted by 1. It turns out it's really convenient to shift the factorial function by 1. I know some of you have taken probability with me. If you haven't and you want a copy of the book, let me know. I go through lots of different arguments about the gamma function and special values, special functions. It turns out gamma of 1/2 is a very special function, and there are ways to compute it elementarily. The gamma function is related to moments of the standard normal. So moments of the normal, so the nth moment would be the integral from minus infinity to infinity of x to the n 1 over square root of 2 pi e to the negative x squared over 2 dx. I want to convert this to a special value of a gamma function. So I have an e to the negative x. I have an e to the negative x squared over 2. I want to somehow convert things. So a good choice is to let u equal x squared over 2. That will give me an e to the minus u. I'm going to have a cost in terms of x's. Well, but powers of x's will just come in like that. So if I take u equals x squared over 2, du is going to be 2x dx over 2. Oh, good, that's just going to be x dx. So that means u is equal to x inverse du. What's x inverse? That's going to be 2u to the minus 1/2. So dx is 2u to the minus 1/2 du. I move the x over the other side. Dx equals x inverse du. If I solve for x, x equals square root of 2u. So since it's an inverse, it'll be negative 1/2. I have to be a little bit careful with this integral. What's bad if I try to do the substitution now?
You still have the x then, right?
No, I mean, if I do this, I now have the integral x to the n
Oh, right.
will become 2u. So this will become 2u to the n halves, right? 1 over square root of 2 pi e to the negative u. And then I'll have a 2u to the minus 1/2 to u. That's looking fairly good. What's the problem with this? Looks reasonable to me. Why is this a potentially bad substitution? There is one thing I have not written in this integral. What's missing? I need words. But yes, you're correct.
The limits of integration.
So what are the limits of integration?
Negative infinity squared divided by 2.
Okay, what's negative infinity squared divided by 2?
Yes, infinity.
Infinity. So I'm integrating from infinity to infinity. Ugh. All right, this is bad. So this is an opportunity to talk about something which I'm sure was emphasized at great length when you were taking calculus many years ago. When you have a change of variables, you want to make sure it's a one-to-one map. This maps 2 points to the same point. All right, what I need to do is I need to say, look, if n is odd, what's this integral? If n is odd, this integral is? What kind of integrand do I have if n is an odd number?
Is it odd?
If n is an odd number, say n is 1, 3, 5, 7, what can you tell me about this integrand? What kind of function is it? It's an odd function. So if you integrate an odd function over a symmetric interval, what do you get? You get 0. So we don't need to worry about this for n odd. For n odd, the moments are just 0 because it's symmetric. So I might as well assume n is even. Okay? Well, because it's even, I can now go from 0 to infinity and double it. And now if I do that, then everything is okay over here. Because now that I'm going from 0 to infinity, no problem. And so now what I get when the dust settles is I have, now this is a 2 to the n. I have a 2 here, and I have a 2 to the negative a half. So it'll be 2 to the n plus a half, integral from 0 to infinity. I have a 1 over square root of 2 pi, I guess, outside. E to the minus u. I have a u to the n minus a half. I'm going to write this as u to the n plus a half minus 1 du. I'm adding 0. The reason I want to write it like that is my expression is of the form s minus 1. And so if I write n minus a half as n plus a half minus 1, it now is in this form, and this will just give me 2 to the n plus a half, 1 over square root of 2 pi gamma of n plus a half. So in particular, if we take n equals 0, that's going to be the normalization factor, and that'll give you the gamma of a half. So it turns out that the moments of the normal are related to the gamma function. They're related to the values of the gamma function at half integers. And if we had ways to calculate that, we'd be in great shape. Okay? Any questions on what's going on here? This is only useful if we have formulas for the gamma function. Otherwise, I've reduced an integral that's hard to another integral that's hard. But fortunately, we actually have nice formulas, especially for gamma of 1/2. It turns out that there's some beautiful gamma identities that give you gamma of 1/2.
What's the use? This is probably a very stupid question, but what's the use of the higher moments of the normal? Like I see till 1, 2.
Well, so the first, since all the odd moments are 0, you can always adjust your distribution to have mean 0, then adjust it to variance 1. So the fourth moment is the first one that really starts giving you information about the shape. The higher moments tell you just how fast things are decaying. And so because the moments of the normal, because of the decay, it gives you some information about how the probability is going. The goal is to have something similar to Taylor series. If you know the Taylor coefficients, you hopefully know the function. If you know the moments, you hopefully know the probability distribution. Unfortunately, that's not the case. There are probability distributions that have the same sequence of moments, but are different. So this is related to a wonderful question, can you hear the shape of a drum? So if you can hear the different frequencies, the different vibrations, the different noises a drum makes when you strike it, the different resonances, is that enough for you to uniquely determine the shape of the drum that can be producing these? And the answer is surprisingly no. So it's a big question in mathematics When does a certain spectrum, when does a certain sequence of values uniquely specify what's going on? The moments are not quite enough. You need a little bit more. You need a sequence of moments that converge to a point. And so because these are just integer valued moments, it's a discrete sequence that's always well separated. There's nothing, however, that tells me I must take n to be an integer. I could take n to be any rational. I could even take n to be a complex number. And you can talk about complex moments. And we do this all the time because then the tools of complex analysis are at our disposal. And when you do that, if you have a sequence of moments, complex moments, that converges to a common point, and if two functions agree for that, then there's a unique density. And so the standard example of two probability distributions with the same moments but different density, they agree at all moments that are integers and half integers, but just those. And that's where things break down. So these higher moments give us information about shape. So right now, this is merely just converting the Gaussian integral to another type of integral problem. Yes?
So the definition of like the nth moment is that you take the probability distribution multiplied by x the n.
Yep. Yep.
So the first one.
Right. So we'll often write it as the expected value of x to the 2n, because we're doing the 2nth moment here. Yep. And the hope is that if you know the moments, you know the distribution. If your distribution is finitely many point masses, if it's 12 point masses, you only need the first 12 moments to uniquely determine it. But when you have an infinite distribution, that's continuous distribution, then it's a little bit more complicated. All right, so the last thing which I'm going to just note is it turns out this equals 2n minus 1 double factorial. So the double factorial means every other. So 5 double factorial is 5 times 3 times 1. 6 double factorial is 6 times 4 times 2. So the factorial is you multiply every term until you come all the way down to 1. The double factorial is you multiply every other term. Could you have defined 5 factorial to be the factorial of 5 factorial? Absolutely. You have your freedom to choose definitions. It's just what arises in mathematics. There's very few times when we take the factorial of the factorial. You want to talk about a function that grows rapidly, the factorial of the factorial grows rapidly. Fortunately, there aren't that many cases where we need to deal with something that's this explosive. But every other one occurs many times. It comes up in a lot of combinatorial problems. And one of the reasons it comes up so often is because these are the moments of the Gaussian. So with a little bit of work, you can prove that these are the moments. So how would you do this? How would you calculate the moments of this? What would you like to do if you had to do this integral directly? It can be done directly. Yeah. So if you want to integrate by parts, you have to choose what's your u and what's your dv. So claim the integral from 0 to infinity times 2 of x to the 2n 1 over square root of 2 pi e to the negative x squared over 2 dx is 2n minus 1 double factorial. So we have to choose what we want u to be and what we want dv to be. Any thoughts on what dv should be? Okay, e to the negative x squared over 2. So if this is your choice of dv, you would need to find something that has that as its derivative. Do you know anything that has that as its derivative?
The same thing multiplied by.
No, because if you start off with this, when you take the derivative, you get a negative x that comes down. You could make this your u, but then if you made that your u when you take the derivative, you would increase the exponent of x by 1.
You just take an x.
You borrow an x from the x to the 2n. And then here you'll have an x to the 2n minus 1. And by borrowing that x, now you can say v is negative e to the negative x squared over 2 And u is going to be 2n minus 1 x to the 2n minus 2. So now you've got your uv, your boundary term vanishes because polynomial growth, exponential decay beats polynomial. In fact, this is beyond exponential decay. So the boundary term is gone. So it's going to equal 1 over square root of 2 pi minus v du. The minus signs cancel, and we'll have a 2n minus 1 coming outside from this, integral from 0 to infinity of x to the 2n minus 2 e to the negative x squared over 2 dx. And if you want, in hopefully clear notation, in is going to be 2n minus 1 in minus 1. And we can see we have a recursion relation. And so I've gone down 1 here, and I have a 2n minus 1. This went down by 2 here. So with a little bit of algebra, you get in is 2n minus 1, and you'll have 2n minus 3, all the way down to 1. You just keep applying this relation. Now when you apply with n minus 1, you get 2 times n minus 1, which is 2n minus 3. And you just march down. So this is a nice way to calculate the moments of the Gaussian by induction. OK. Any questions on this over here? All right, so now it's time to start calculating the Fourier transform. OK? So to calculate the Fourier transform of the normal, we should really do the Fourier transform of not just the standard normal, but an arbitrary one. If we can do the standard normal, we can just go back into the calculations and bookkeep and put in the standard deviation. I want to keep the calculation as simple as possible. We're going to have more than enough letters and symbols floating around. So I really want to show how to do these calculations. I thought long and hard it was somewhat fortunate that my son had a soccer game that was essentially canceled because no one from the other team showed up. And so I've come up with 2 calculus proofs for this. There is the complex analysis proof. And so I will sketch the complex analysis just because it's nice to be aware of what can go on in complex analysis. But we will not really be able to use that in this class because complex is not a prerequisite. So this is meant to be a real fast, high-powered sketch. And a motivation, if you want to go to pure math grad school, or maybe physics grad school, something like that, complex analysis is one of the courses you need to use. So Fourier transform of normal 0, 1 via complex. So we need to integrate from minus infinity to infinity of e to the negative x squared over 2 e to the negative 2 pi I tx dx. What we're going to look at instead is what's called the moment generating function. And this is just the expected value of e to the tx, which is the integral from minus infinity to infinity of e to the tx times our density. 1 over square root of 2 pi. I dropped the square root of 2 pi. E to the negative x squared over 2 dx. So we need to calculate this integral. Turns out this integral is not that bad to do. We complete the square. So this is the same as 1 over square root of 2 pi, integral minus infinity to infinity, e to the negative 1/2. We have x squared. When we bring this inside, what do we get? We get a minus 2tx, right? So if you want to complete the square, what would you like to have after the minus 2tx? So we want to complete the square. What do we need?
Plus t squared.
So we have plus t squared. Are you allowed to just add in a t squared because you feel like it? No. So what do you have to do if you've added t squared? Subtract t squared. dx. So this is, I can pull out the e to the negative 1/2 negative t squared, and I'll get an e to the t squared over 2, 1 over square root of 2 pi, integral from minus infinity to infinity, e to the negative x minus t squared over 2 dx. But what is this integral? What does this integral equal? It just equals 1. It's a probability distribution. It's a Gaussian with variance 1 and mean t. Or if you want, just change variables. Let u equal x minus t. So this is just e to the t squared over 2. And so now, this is where complex analysis is a very different subject than real analysis. In complex analysis, if two functions agree on a sequence of points that accumulate, and the function is differentiable, then the functions are equal. This is a strange result. If two complex differentiable functions agree on a sequence that accumulates, then are equal. To convince you that this is shockingly different than real analysis, consider the following functions. F of z is identically 0, and g of z, I'm sorry, we're doing functions of a real variable. These should be x's. F of x is 0, and g of x is x cubed sine 1 over x. This function's oscillating heavily, but as x goes to 0, sine of 1 over x is between minus 1 and 1. X cubed is going to 0. This will just go to 0. So we can define this, if you want, with a split definition. We can define this to be 0 at 0. It turns out this function is differentiable once. The x cubed is so nice that even when I differentiate, I get a 1 over x squared coming out from this. The x cubed is enough to survive that. These two functions agree on infinitely many points on a sequence that accumulates. The sequence accumulates at 0. But these functions are not equal. It turns out in complex analysis, if you're differentiable once, you're differentiable infinitely many times. And the reason is complex analysis is a very different subject than real. In real, if you want to take a limit, it's boring. Go down, go up. Those are your two paths. In complex analysis, to say a limit exists, you can take paths like this. And no matter what path you take, you must get the same result. So this is supposed to be a senior seminar. I'm supposed to recap some of the things you've seen early in your career. I will use the optimistic phrasing. I'm sure you remember from Calc 3 when you talked about directional derivatives. It's not enough for the function to be differentiable for the directional derivatives to exist coming down along the coordinate axes. You needed a little bit more than that. Just because the derivatives exist along the coordinate axes does not mean you get the same answer no matter what path you take. For complex analysis, you've got one variable, z equals x plus iy. If the derivative exists, it means a lot more than in real analysis because you're saying no matter what path you take, you always get the same. And it turns out any function which is complex differentiable once is complex and differentiable infinitely many times. And if you agree on a sequence that accumulates, you must be identically the same. Why is this useful? Well, let's consider the function mx of t, and let's consider the function e to the t squared over 2. Do these two functions agree whenever t is real? Isn't that what we just showed? So these two functions agree whenever t is real. This function, it turns out it's defined even if t is complex. The imaginary part here is going to have absolute value 1. The integral will still exist. With a little bit of work, you can show that this function is complex differentiable. So what you get is you get the moment generating function of z must equal e to the z squared over 2. And now just take z to be negative 2 pi I t. And then e to the z squared over 2 becomes e. We square the negative, becomes a positive. We square the I, becomes a negative. So we have a negative. We'll have a 4 over 2 is a 2 pi squared t squared. And that's the Fourier transform of the Gaussian, of the standard normal, e to the negative 2 pi squared t squared. And we got it from this beautiful result in complex analysis. We knew these worked for real values. So the functions must be equal for all values where they're both defined and differentiable. This is defined and differentiable for all z. We're done. Okay? This is a major result. Now, it's not surprising that we might want to use results like this. The Fourier transform involves exponentials. It involves complex numbers. A class like complex analysis is probably useful for something like this. This course does not have complex analysis as a prerequisite. So this, I'll leave it as it's an interesting challenge as a lecturer. You know, I can't use a result like this. I want you to at least be aware of this and have some sense of the beauty and the power of complex analysis. But we've got to be able to prove all of these results using just real variables. So this will allow me to show some really nice tricks and techniques of real integration. And these are worth knowing how to attack problems like this. These are good things to have in your arsenal. To some extent, we might be mimicking what's lurking in the background in complex analysis. But it will allow me to review some of your good results from real analysis. There's a great quote that, frequently the shortest path to a theorem in real numbers is through the complex plane. Is you go up to the complex plane, use those powerful techniques, and then reduce downward. All right. So real proofs of the Fourier transform of normal 0, 1. All right. So let's integrate from minus infinity to infinity, 1 over square root of, let's just go from, well, we'll do it slowly. E to the negative x squared over 2, e to the negative dx. So this is not quite the Fourier transform. If it was the Fourier transform, I should really have negative 2 pi t. All right, if you really want the Fourier transform, replace t with 2 pi, at the end of the negative 2 pi at the end of the day. I am trying to cut down on the symbols that are floating all over this. All right? How can we rewrite e to the itx? When you see e to the itx, how should you think about representing it? What's your first thought when you see this? Euler's theorem. So this is cosine tx plus I sine tx. What's the integral of this function times the sine? The integral of the Gaussian times the sine is what? It's odd. So what's the integral of an odd function over a symmetric interval? 0. So this is just double the even from 0 to infinity. So this is 2 over square root of 2 pi, integral from 0 to infinity, e to the negative x squared over 2 cosine of tx dx. All right? When you see cosine, do you think of anything about cosine? Do you know any formulas for cosine? How would you compute cosine? Oh, you actually want to replace this with an infinite sum? All right, let's do it. So square root of 2 over pi, integral 0 to infinity, e to the negative x squared over 2. Now we'll have a sum, and goes from 0 to infinity of negative 1 to the n tx to the 2n over 2n factorial dx. What would you love to do at this point? When you have something like this, there's only one thing you can do. Switch. So to justify the switch, you have to show that the integral sum of the absolute values is finite. Then you can use Fubini's theorem. So I will just do the switch, and then at the end of the day, I will put in absolute values and convince us that it does still converge. So we'll temporarily assume that we can switch, and we'll show later that it's actually justified. So we'll have square root of 2 over pi. We'll have a sum, n goes from 0 to infinity. We'll have an integral from 0 to infinity. I'm going to write this as x to the 2n e to the negative x squared over 2. Actually, I'm going to keep the 2 outside over here, and I'm going to bring back over here the 1 over square root of 2 pi dx. And then we'll have negative 1 to the n t to the 2n over 2n factorial. Why do I want to write the integral like this? What is this equal to? Yeah, the 2nth moment. In a non-temporary, really good classroom with lots of horizontal blackboard space in the main wall, we would actually still have the moments on the board. This is just 2n minus 1 double factorial. So we get 2, the sum n goes from 0 to infinity. We'll have 2n minus 1 double factorial over 2n factorial negative t squared to the n. Okay. 2n minus 1 double factorial is all the odds. 2n factorial is all the numbers. So if I take all the numbers and I remove the odds, what am I left with? Evens. And so I can write the evens as 2, 4, 6, 8, all the way up to 2n. For each even, I pull out 2. And so I get 2n times, and I have 1, 2, 3, 4, 5, all the way up to n. So after a little bit of algebra, this is just 2. The sum n goes from 0 to infinity of negative t squared to the n. And then I'll have 2 to the n factorial. Oh, but wait a minute. If I've got a 2 to the n, and I've got a negative t squared to the n, what should I do with that 2 to the n? What should I do with that 2 to the n? How should I rewrite this? So I used 2n minus 1 double factorial over 2n factorial is 1 over 2 to the n factorial. How should we combine? We've got negative t squared to the n over 2 to the n factorial. This is the same as 2 sum n goes from 0 to infinity of negative t squared over 2 to the n over n factorial. Do you recognize that function? What's that function equal to? And there's the Fourier transform. Now all we have to do is justify that the integral sum is the sum integral. Well, if we put in absolute values, the negative t squared just becomes a t squared. This just becomes a t squared. This just becomes a t squared. Everything's fine. Absolute value is OK. We're done. So in some sense, what this is doing is it's mimicking the expected value of e to the tx. We have to do a little bit more work, but we've got it. OK. Any questions about this?
So your absolute value, you mean taking the absolute value of this sum?
So So I would take the absolute, right, because this is non-negative, so I'd have the absolute value of the sum. By the triangle inequality, that's less than equal to the sum of the absolute values. The sum of the absolute values, all that happens is I drop the negative 1 to the n, and I get something that's finite. And so because it's finite, I can then use Fubini and switch the order of integration. Okay. We have time for one more proof. Okay. Any questions on this one?
Is this what we were supposed to do on the homework?
Yes.
Prove this?
Yes. Yep. It is possible to do it using real analysis and using the stuff you have known up till now. It's not easy. Part of this is to really show you the powers of complex analysis and to give you an appreciation of how difficult some of these calculations are. The Fourier transform is useless if we can't calculate it. Right? So how do you calculate the Fourier transform? Okay. So in terms of what I expected you to do on the homework, I'm not expecting anyone to have seen something like this. If anybody saw this, this is phenomenal, and when I write letters of recommendation, I will mention it. In terms of what grade should be, I'm not expecting anyone to have gone in these. It's meant to just really give you a sense of appreciation for these techniques. All right, let's do one last technique. Let's let I of t be the integral from minus infinity to infinity, 1 over square root of 2 pi e to the negative x squared over 2 cosine tx dx. We already know that it's enough to do this. Okay. I'm going to differentiate under the integral sign. In your real analysis class, did they prove to you when you can differentiate under the integral sign? So this is a great result that you should have seen. What you could do is you could look at I of t plus h minus I of t divided by h, go through, expand things out, and justify that the differentiation is permissible. In the interest of time, I'm not going to bother doing that right now. If people want, email me or just tell me, and I will justify this at the start of next class. For now, let's just assume you can interchange the derivative in the integral. So we would get I prime of t is the integral, and I might as well go from 0 to infinity. Or do I want to do it this way? No, I'll keep it this way. Integral from minus infinity to infinity, 1 over square root of 2 pi e to the negative x squared over 2. And now I take the derivative of cosine tx. And the derivative of cosine tx, derivative of cosine is negative sine. I'm taking the derivative with respect to t, so I get an x coming out. And it'll be negative x sine tx dx. I could try differentiating again, because then I would get a cosine term, and I'd get back to what I started with. Maybe I could do like a bring it over method. The problem is I'll have too high of a polynomial, and the integrands won't match. So doing another derivative is bad. However, when you look at this, what do you want to do now? When you look at this integral, what would you like to do?
You could do it by parts.
Yeah, you can do it by parts. U dv will be e to the negative x squared over 2 negative x dx. We'll put the negative sign there. U will be the sine of tx. Du, we're taking the derivative with respect to x, is going to be t cosine tx. And v is going to be e to the negative x squared over 2. The reason I'm keeping the integration from minus infinity to infinity is I don't want to worry about any boundary terms. The boundary terms vanish again, and I'll have minus v du. So I get I prime of t is going to be the integral from minus infinity to infinity, 1 over square root of 2 pi e to the negative x squared over 2 t cosine tx. And there's a minus sign. What should I do now? How do I handle this integral? So much of math is pattern recognition.
Well, you have
Mm-hmm.
I of t. by the integral, like
Multiplied by what?
t.
By t. I just pull out the t. I'm integrating with respect to x. Pull out the t, and then I just get I of t. So I get I prime of t is minus t times I of t. I just have to solve this differential equation. Right? We should know how to solve, differential equations like this. It is not a requirement to graduate from, Williams math knowing how to solve differential equations like this, but you should. All right, so there's a lot of ways we can look at this. So we have I prime of t over I of t is negative t. This is d by dt of the log of I of t is negative t. Because the derivative of the log is 1 over I of t, I prime of t. So when I integrate, I get I of t is negative t squared over 2 plus a constant. I'm sorry, and this is a logarithm. Oh, okay. If the log of I of t is this, then I of t is going to be e to the negative t squared over 2 e to the c. All we have to do is figure out what that constant c is. How should we figure out what that constant is?
T equals 0.
Take t equals 0. So when we take t equals 0, then we come back to I of 0. Well, I of 0, cosine of 0 is just 1. That's just the integral of the normal, which is just 1. E to the negative t squared over 2, this is equal to 1 when t equals 0. So e to the c has to be 1, so c has to be 0. So as I of 0 equals 1, we get I of t is e to the negative t squared over 2. And this is another elementary proof of the Fourier transform of the Gaussian. This idea of taking a derivative under an integral sign and then doing some non-trivial work. I mean, what's phenomenal about this is we can just pull out the t at the end of the day. And we just get back, minus t I of t. It's hard to underestimate just how powerful of an observation this is. You want to get somehow relations connecting your unknown quantity, and then close cousins of it. So these are really good techniques. Hopefully you've seen something like this, solving differential equations like this. It's often done in Calc 2. I have to say often because I've never actually taught Calc 2. And given that I've been in academia for more than 2 decades, my goal is now to make it through my career without ever teaching Calc 2. I never want to teach that class because I've made it so long. I've done Calc 1, I've done Calc 3 more times than I can remember. But I've been told that you do stuff like this now in Calc 2, solving systems like this. Or if you're taking some mathematical bio or differential equations, you'll see something like this. You want to know how to solve simple differential equations like this. And this gives you a phenomenal technique. So what this is telling us is we actually have some ways to calculate Fourier transforms using just real variable techniques. And now that we know the Fourier transforms, we can actually use those for Poisson summation. We can use those to attack a lot of problems. So Poisson summation is just a phenomenally useful tool. It takes frequently a long, slowly decaying sum and replaces it with a rapidly convergent sum where frequently just the 0th term is enough. But if we can't calculate the Fourier transforms, it's not useful at all. We've seen for Fourier series, we had Dirichet's theorem about pointwise convergence. We had Bessel's equality or Parseval's theorem, which we could use to then evaluate some infinite sums. So one of the goals of this class is to see how these different materials connect and allow you to replace some expressions. My physics mentor from my undergraduate days, Frank Firk, he knew his trig identities up to cosine and sine 10 theta. And in the years before Mathematica, before symbolic computer programs, to be able to look at the horrible physics expressions and see how things simplify is extremely important. So looking at some expressions like this and seeing what's really going on, how do you pull things out, it's highly non-trivial. And that's one of the things I want you to get out of calculations like this. Okay, because we've now paid the piper and had 2 very technical lectures with a lot of stuff like this, on Wednesday's lecture, what I want to do is I want to bypass all of this and show you how we could have avoided Poisson summation and use specific properties of the Gaussian to prove that a normal with spreading variance mod 1 becomes uniform. And again, we can do this because we know certain things about the Gaussian. And so frequently, if you want to use properties specific to what you're looking at, you have different types of proofs. But it's nice to know which proofs work in general. Okay.